going to give you really as much practice as we can. This is the beginning, but there are other things we're going to learn. Essentially, we're going to get a stupid thing. Sassing, frassing. I'm having Windows issues. There we go. I'm trying to shove this window as far away so it doesn't bug me anymore. Ooh, that's good. Right. So we're going to look at sampling distributions. I've reduced the questions because we definitely weren't going to get it all done. So I kind of halved it in two. And so it's going to be called sampling distribution proportions A. And then next week we'll do the other half, which is proportion B. And essentially we're looking at the fact that if you take lots and lots of samples, you get a distribution which is called sampling distribution. And it looks like this. And right in the center, the mean, it's equal to P, which is the population proportion. And not only that we can actually get its standard deviation. And its standard deviation is given by this formula. Now, there's really two, to be very specific, there are two situations. There are going to be questions where they tell you the population value. They're going to tell you the population value and they're going to tell you P. And they tell you it's 0.3. And they're going to tell you that the sample is, say, 105, just to be awkward. In those questions, the mean of this sampling distribution, which is what we call this thing, what you would get if you took lots and lots of samples from a population. The value that you would get would vary. Sometimes you get more, sometimes you get less. But the mean will be P, and the standard deviation will be this guy. And P is just simply the number they give you. And the standard deviation is going to be 0.3 times 1 take away P, which is 0.7. And then it's going to be divided by 105. And if we go here and they do a square root of 0.3 times 0.7, and you divide it by 105, the answer you get, let's say to 3 decimal places, is that. So if you imagine this would be a picture of it, the most likely sample you would get would be 0.3, but can you imagine going 3 standard deviations, going 0.05. So this guy would be 0.345 and so on and so on. What that allows us to do is to get a kind of picture of, for a sample of say 105, what kind of variation do you get in your sample? Is your sample likely to be close to the real answer, or is there a big chance that it might be quite far away, right? It's a kind of way of trying to measure the error, how likely it is to be good. Now, it's more likely than not, isn't it, that you don't know the population proportion? Because why would you bother taking a sample if you already knew what the answer was, right? So the more realistic situation is you don't know that. But we can estimate it by getting P hat. And isn't P hat the sample proportion, right? What the people in your sample did. So in this story, the mean that you get is P hat, and this guy is called the standard error. And if you look at it, you see it's essentially the exact same formula, but instead of using the P that they give you, they use the P hat. So an example of that might be something like this. You conducted a survey of 1,000 people and you found out that 0.53 said they were going to vote Republican. Now, in that world, the sampling distribution, or at least my best estimate of it, would be 0.53. And we call it the standard error, which is essentially still a standard deviation, but we call it a standard error to distinguish it a little bit. And it's going to be 0.53. Take that away from 1 and you get 0.47. And then you divide it by 1,001. And we get the square root of 0.53 times 0.47 divided by 1001. And that comes out to be 0.016 to 3 decimal places. And you know I like percentages, so I would say that your best guess is about 53% of the people are going to vote Republican based on your sample, and the range or the error is about 1.6%. Okay, so it's not very scientific yet. We're going to improve on this, but are you beginning to get an idea that this number gives you a kind of measurement on how reasonable to look at this? Imagine I had a story where I went and said, I collected a sample and 0.25, right, which is 25%, said they like Pepsi. And the standard error was 0.11, 11%. Would you agree that 25%, give or take 11%, is a pretty big range of places for the real answer to be? And therefore, I wouldn't be paying that much attention to it, right? Imagine a same storyline, but the standard error was 1.1, right, percent, which would be 0.011, right? Now, 25%, give or take 1.1%. Are you beginning to feel a little bit more confident that that estimate's probably pretty close to the real answer? And just take it to extremes. Suppose it was 0.00011, which is 0.011%. If this was the answer that came out and this was your error, wouldn't you maybe not bet your house on it, but wouldn't you be very comfortable that the answer's darn close to 25%? Not a lot away from it, right? And now we're going to improve on this number, this error number. But right now, if you're wondering why am I even getting the standard error, it's a number that's giving us a clue to how accurate this sample is, right? How likely is it to be true, right? Close to the real answer. Are we comfortable about these two formulas and how you would do them? Okay, so what I'm going to do is I'm just going to pick maybe a question like this and maybe one or two like this, and then we'll move on to the final stage, which is to put a little bit more meat on the error thing. And here we go. I've lost the damn thing. What happened to you? Oh, that was weird. Okay, found it. So, if you get a question like, let's do one with P in it. Right. Suppose you get a question like 2B, and they tell you that the sample is 1,344, and that P is 0.3. Would you agree in this question then, this is a population number, because it's P, right? It's a parameter. And you're being asked to get the mean. The mean is going to be P, isn't it? So that answer is going to be dead easy. And since this is a population, we'll call it standard deviation. Won't it be P, 1 take away P over N, which in our case is going to be 0.3, 0.7, all divided by 1,344. At this point, my calculator is going to come in, and well, I was looking for accuracy. I can't see it. I'm sure it's in there somewhere. So 0.3, square root of 0.3 times 0.7 divided by 1344, finish the brackets. Ah, that's why there is no accuracy, because the answer is actually an exact value, right? And that's question 2B finished. If they tell you these and ask it to find them, isn't it just plug and chug? Right? Find the formula, plug it in, hit some buttons, and you're good to go. They're giving us no reason right now why you want to do that, but it's going to be connected to accuracy, as you'll find out later. So let's do one with a p hat in it and see if we can do something about that. This is question 3C. In question 3C, you are told that there was 1,000 drivers and you got, oh, they're a little bit different. You asked these 1,000 drivers, do they wear seatbelts? And 150 of them says, nope, I never wear a seatbelt. We'll assume that they're telling the truth, which is surprising, but nonetheless, that's what they said. I'm not even sure why I need a calculator for that. Would you agree that this guy is 0.15? So maybe sometimes you have to actually calculate p-hat, you know, because they don't just give it to you. Well, I've got everything I need because they're only going to ask me two things right now. What's the mean and what's the standard error? Can you see that because it's a p-hat, it's the standard error we're going to call it, even though the formula is identical? The mean, nothing 0.15. The standard error is going to be p-hat, 1 take away p-hat over n. So it's going to be 0.15, 0.85, 1 take away that, over 1,000. And this time, see what we get. Square root 0.15 times 0.85 divided by 1,000. And the answer is 0.4 decimal places in one. So 0.0113. And there is your standard error. Do you need any more of these? Are you comfortable about how to find the mean, standard deviation if it's a population question, or the mean and standard error if it's a sample question? Are we good with that, or do you want to say another one? Can't really tell. Are we good? Okay, I got a nod. Finally got some feedback. So, can you remember the 68, 95, 99.7% rule? Remember that guy? We are going to use that guy to help us create what are called confidence intervals. Now, they will use the word empirical rule. So when you see that phrase, they're talking about this, right? That 68% of the data is one standard deviation away from the mean. 95% of the data is 2 standard deviations away from the mean. And 99.7% is 3 standard deviations away from the mean. You remember that? 1 standard deviation, 2, and 3. It's called the empirical rule. And we are going to find that to get what is called a confidence interval, right? And although at this point in time, they're not calling it that, that's what it is, right? So let's suppose that I conduct a sample and my sample has 200 people in it. and I ask them, what shall I ask them? I ask them, what do you like pickles? And 0.35 of them in my sample of 200 says they like pickles. And my random sample of 200 is a fair representation of Americans, right? We'll take that for granted. What I'm going to do now is I'm going to create a 99.7% confidence interval. Essentially, what I'm going to do is I'm going to create an interval, and the numbers in that interval, I'm 99.7% the true population number is. Would you agree that that 0.35 is just a snapshot of 200 people I picked? It might be quite close to the right answer. It might be a bit far away. It depends on how much error there is in the process, right? But we are going to collect a 99.7%. And the formula for it is, well, let's put it in English. It's the mean plus or minus 3 standard deviations or standard errors. Depends on the question. If this is a P, it'll be standard deviations. In this case, would you agree it's a standard error? It just being fussy about the naming. Although in my brain, they're both standard deviations, but just to keep things cool. Now, if that's P hat, what's the standard error going to be? Well, it's the square root of P hat 1 minus P hat over N. It's a square root of 35, 65, all divided by 200. So let me see what that comes out to be. So you go square root 35 times 65, and you divide it by 200. Oops, too many. 200, and you get the answer 0.03. Yeah, we'll do it 33. Okay, so it's 0.03. So a 99.7 is the mean, plus or minus 3 standard errors. So the mean is 0.03. No, it's not. The mean is 0.35. Plus or minus 3 lots of 0.03. So that's 0.35 plus or minus 0.09. And I'm running short of room, so I'm putting it up here. 0.35 take away this guy gets you 0.26. And 0.35 add that guy gets you 0.44. And if you like percentages, which I do, that's 26 to 44%. So if I pick a sample of 200 and I think that my sample says 35% of them like pickles, my prediction is that the true answer to the entire population of America is somewhere between 26% and 44%. Why is that interval so big? What do you think the practical reason for this being so big?
The small number of the sample.
Yeah. Well, it makes sense if you only pick a small sample. Shouldn't you be expecting a lot of things could happen, right? In a small sample, a lot of things will happen. And 200 might seem reasonable to you, but it's not that big. And we got this Scylla. So let me pretend that in an alternate universe, it wasn't 200 people that we asked, but it was 20,000 people. And we still got 0.35, right? Let's see what the confidence interval for this guy would be. Would you expect this to be a much smaller interval based on the fact the sample's so big? And it will be. Let's see how much smaller, right? Well, I need to calculate the standard error, so I'll do that right now. So it's going to be 0.35 times 0.65, but now it's going to be divided by a much bigger number. So I'll go into my calculator and I'll just add 2 more zeros. And the answer I get is 0.003 if you round off. And a 99.7%. Would you agree a 99.7% is pretty close to, I'm almost certain the right answer is in this interval somewhere. It's not a perfect thing, it never will be. And so we're going to get this guy, and it's going to be the mean plus or minus 3 lots of this guy. So it's going to be 0.35 plus or minus 0.009. So it might be 0.341, and it might be as high as 0.359. And I'm turning this into percentages so I can get a better feel for it. Can you see that we are now pretty sure that the answer is somewhere between 34 and 36? Now, one of the interesting things about a sample size of 20,000 is it doesn't matter if the population of America is 3 million or 300 million. This answer is the same, because this answer doesn't care what the population size is. Doesn't this answer only depend on the sample size? Which might seem maybe not obvious, but it's nice to know that, right? I don't care how big the country is. If my random sample is a fair reflection of Americans, and I pick 20%, 20,000 of them, I can be darn close to the right answer. Now, of course, there's a little devil in the detail. If I'm 99.7% sure that the right answer is probably going to be in this interval, aren't I also 0.3% chance that I'm just wrong? And I could be wrong by miles. The fact you're wrong means it could be anywhere. Couldn't it be as much as 90% like pickles to 1% likes pickles? It could be anywhere in the world. So when people make predictions on elections, for instance, which is going to be my next story, they are going to get that prediction wrong at least once or twice. And people think, well, you predicted it was going to be a Republican and a Democrat one. There's something fishy going on. Or you said it was going to be a Democrat one and then the Republican one. What's going on here, right? It works both roads, both ways. So let's have a story about a fictitious governor's election in some place that might be happening soon. And I'm going to make up my own data. That way, life is simple. And there was 1,010 people in my sample. And my sample was a fair representation of people in this state. And we asked them, are they going to vote for the Democrat, right? And the answer that they got for the Democrat was 0.51, which is 51%. And people say, the latest poll, the Democrat's going to win, right? He's got 51% of the votes based on our sample. Well, let's take this a little bit further and see what we want. Do you want a 99.7? Let's change it to a 95% confidence interval, right? Just to be different. So the standard error is the square root of p hat 1 minus p hat over n. Now, what I'm showing you right now, with the exception of the number, right, that I made up, but the process I'm about to do is the exact process that they are doing, right? I can tell you that right now. right? So they went out and they asked whatever number, and 42% or 59% said, I'm going to vote for the guy, right? So if we pretend that that was true data, everything from this point onwards is realistic. So it's going to be 0.51 times 0.49, and it's going to be divided by 1,010. Actually, that number is pretty accurate. The typical sample size is 1,000 and change. They normally do just a little bit over 1,000 in case some people say, I'm not going to answer the question, right? They kind of like 1,000 as a kind of number. So they might have asked 1,050 people, but 1,010 answered, right? So let's move on. The square root of 0.51 times 0.49 divided by 1,010 ends up being 0.016. Now, to be a 95% confidence interval, isn't that 2 standard deviations away from the mean? So it's going to be the mean plus or minus 2 standard errors, which is what we call them. So it's going to be 0.51, give or take 0.016. If you take that away, you get 0.494, and if you add it, you get 0.526. And since I like percentages, 49.4% to 52.6%. Now, the real answer to how many people are likely to vote for the Democrat guy in this election, we are 95% sure it's probably in this range. Do you notice that this range has numbers less than 50% and numbers that are bigger than 50%? And every single one of those numbers is just as likely as any of the others. So don't put any particular strength on that one, right? 49.4% is just as likely as 51, and so is 52.6%, just as likely as 51, right? So every number in this range is equally likely as any other number in that range. Based on this interval, wouldn't the answer, or it should be at least, shouldn't they say that? Too close to call. Right? That's kind of the standard political jargon for it could go either way, right? Now, you see this guy here, which is what, 1.6%, if you turn into percentages. This guy has a name as well. He is called the margin of error. Have you ever heard of them? They'll say it's 42% and the margin of error is plus or minus 3%. And you wondered where the plus or minus 3%, or in this case, 1.6 came from. You now know, don't you? That's how they, this is the calculation. You could do it yourself. If you know how many people are in the sample and you know this number, can't you calculate this on your own? And you'll be able to tell if it's a 95 or a 99.7 that you use. And when they, sometimes instead of too close to call, they use this phrase instead. They say within the margin of error. Have you ever heard that phrase also being used in these questions? So if you're wondering what that's about, does this question kind of put some meat on the topic now that you know what they're doing and how they're calculating? They're just asking 1,000 odd people, who are you going to vote for? And then from there onwards, whatever that number is, isn't the rest pretty standard? And there are rules to what you can and can't do. You know, you shouldn't be allowed to, and no statistician who's honourable would ever do it. You're not allowed to do a 93.5% confidence interval or some weird number that you just plucked out of the air, right? Actually, the most standard ones are not 99.7 either, but this book's starting with that, and then later on we'll show you that they refine it. The real numbers are 90, 95, and 99. They're the three typical confidence interval boundaries that are used in every statistical survey you're likely to see. There's a 90% confidence interval, a 95, a 99. Sometimes, but only if you're talking nuclear bombs or something, there might do a 99.9% confidence interval. And you know, you'd only do that last one if somebody's life depended on it, so you wanted to be really, really sure that everything was okay, right? But normally 90, 95, and 99. Now, if I did a 6 to 8% confidence interval, would you agree that would be useless? Because wouldn't roughly 1/3 of the time, my answer would be totally wrong. Do you really want to take somebody if 1/3 of the time they told you a pack of lies and the other 2/3 of the times they told you the truth, but you didn't know which it was because they're that good? I mean, would you really want to risk your life or your house or anything on them? So that one is only there for numerical purposes. 95 is a good one. 99.7 right now is taking the job of the 99% that comes later. So it's a little bit more accurate, a little bit safer. Any questions about that? Okay, we got time for one more of these. Let's pick it from the list. Okay. No, I don't like that one. That was too easy. This one is question 8. A medical researcher thinks that P equals 0.7. Okay. And we're assuming that P equals 0.7 and that he takes a sample of 370 people. And let's put the context in here. Suppose the medical researcher thinks that P is 0.7 is the proportion of all teenagers with high blood pressure. Wow. So he thinks 70% of teenagers have high blood pressure. I would be surprised, but whatever. So he collects a sample of 370, okay? And let's see what goes on then. Right, question A asks us to get the mean and the standard deviation. Well, the mean is 0.7 right now, and the standard deviation is 0.7, 0.3 over 370. And so the square root of 0.7 times 0.3 divided by 370. And the answer I get is 0.024 to 3 decimal places. And I'll have to change that, so it's 0.238 because they want 4 decimal places. Okay, that was easy. Isn't that just applying the formula that we already know? And then question B says, use this to create a 99.7% confidence interval. So that's going to be the mean plus or minus 3 standard deviations. So it's going to be 0.7 plus or minus 3 of these guys. I wish they weren't so detailed. So 0.7 plus or minus 0.0238 times 3, and I get 0.0714. So that's going to be 0. I don't know, because too hard to do in my head. So 0.6286, and if you add it, 0.7714. Are we comfortable about that? And then I just realized, because they do this to make my life a misery, that they changed the accuracy for that question to 3 decimal places. Have you ever done that? That you write in 4 and it tells you you're wrong because they wanted 3? You know, be aware of it. Okay, move on to C. In C, they did a clinical trial, right? So a clinical trial had 370 teenagers in it, and 200 of them had high blood pressure. So the sample number is 200 divided by 370. So that's 0.54. What do they want as accuracy? Oh, they want 2 decimal places. Fair enough. And they asked you to find p hat, and I've done it. Is this guy here a parameter or a statistic? Is this p hat a parameter or a statistic?
Statistic.
Right. And so underneath this, there was a little guy, and you said, right, that guy, and not that guy. So far, so good. Right. Now, given the answer to be in Spain, explain why the observer. Oh, so this isn't. Yeah. Okay. This guy is 0.54. Why does it not agree with this? Because isn't 0.54 outside that range? Well, would you agree that it's very rare for that to happen, right? Because we are 99.7%. Haven't we found the 0.3% of the time that you screwed up? Right? That's maybe not very satisfying, but that's essentially what happens. So always don't trust your answer to be the truth. Trust the answer to be the closest approximation to the truth that we can find. But always have in the back of your mind, but I could be wrong. Because would you agree you can be wrong 0.3% of the time? And guess what? This was the time. Which I guess is why gamblers very rarely own mansions. Because in a gambling world, aren't you gambling against the house winning? And the house is almost always going to win. But occasionally, you know, the odd 0.3% of them leave the place up, right? That kind of thing. I'm going to, based on what I've just seen here, yeah, we got time for one last one then. Okay. Which one shall I pick? No, I'm just thinking I'm going to have to reduce the questions, but I'm trying to think of which one I can do. Okay, we can do this one. To finish then, when can you use this process? Right, we're collecting confidence intervals and means and standard deviations and p-hats and making predictions about somebody winning an election or not. We're doing all of that stuff. But we haven't talked about when you're actually allowed to use it. Let's talk about when you're not allowed to use it. Because if you know that, then as long as it's not this list, you can use it, right? So we're doing it from what you can. Any ideas, the first reason or the first situation where you're not allowed to use this process?
If you have a total population,
Say that again, Rob.
if you have all of the population,
Oh, I never thought of one, but I put that one in, yeah. If you ask a census. Would you agree if you ask a census, you know the answer? You don't need an interval
Right.
if you know the answer. Yeah, I never thought of that, but that is a good answer, Rob. Give me another situation where you wouldn't really be comfortable in doing it. I think when I tell you the answer, you'll know what I'm getting at. So it's kind of hard because my question is vague. But what do you think might be a problem?
When the question is too specific?
Not thought of that one. Not necessarily. There are lots of other things like asking a biased question, and I totally agree all those things. The main one that I'm interested in is sample size.
Yeah,
Would you agree it's not a good idea to just ask 2 people who you're going to vote for? Because won't the answer come back? Nobody's voting for the Democrat, 100% is voting for the Democrat, or 50%, right? So we have a test for it. And the test says this: n times p, or p hat, has to be bigger than 10, and n times 1 minus p hat has to be bigger than 10. It's very often called the 10 rule. So it isn't that the sample has to be 10. Actually, the sample has to be bigger than 10. The value of NP hat has to be bigger than 10. So give an example. Suppose I have a sample of 50 people and P hat happens to be 0.3. So obviously N times P hat will be 15. That's good. Won't N times 1 minus P hat be the other 35? So that's good. Suppose I have N equals 50 and P hat is 0.1. Won't N times P hat be 5? And that's bad news. So can you see it's not just the sample size, but it's a combination of the sample size and this guy. Now you might say, but N1 minus P hat is really big, which I totally agree with you. But if one of them doesn't work, don't do it. Analogy. Can you imagine I'm looking for what percentage of Americans have a very rare form of cancer? And I ask 10,000 people, right? I test 10,000 people, and only one of them has that cancer. 1 out of 10,000. Would you agree that that is a very dodgy set of data to try and project to the American population? And the reason isn't because the sample size was small. 10,000 people is massive. Isn't it because the p hat is tiny? The number of people who have that disease is, relatively speaking, very, very small. So if you wanted to know what percentage of Americans had a really rare cancer, wouldn't you probably have to test millions to be comfortable you knew what the answer was? Right? And sometimes it's just impractical. You know, I bet you, I don't know one off the top of my head, but I bet you there's a cancer right now in America or in the world where only 1 in a million people get it. Right? Some kind of weird nail cancer or something, right? Some cancer I can't think of. Wouldn't that be very hard data to collect on what percentage of Americans are likely to have that, right? It's like, in fact, won't half of them not even get diagnosed probably because the doctor has never seen that particular cancer? In fact, aren't some doctors really keen on unusual diseases when they see one? Because the first thing they do is they tell all the, hey, I finally found blah, blah syndrome, right? 30 years in surgery and I finally got someone who's actually got this complication, right? And they do a lovely paper on it and they publish it and they're kind of happy about it, right? They don't do that if somebody comes in with a broken arm, right? I've seen thousands of those, right? So you have to be careful about the sample size, but I do like your census. That's a good one. We'll assume that all the other things are true. You ask the question in a nice, unbiased way, right? You don't say, are you going to vote for that pseudo-communist Democrat guy? That would not be a very good way of asking the question, right? You wouldn't go to a church and ask people there about abortion, right? And you wouldn't go to a country club and ask people about taxes, right? So the people you ask have to be a fair representation. You ask a good question, all the other things, we're just assuming that they're okay. This is just an added issue, sample size, and we have a little test. And some of the questions ask you to do that test. And say your last name and